Hi, I'm Sarah, and welcome to Mathitude's Cryptic Caverns Hacks video. We've heard that the third level of Cryptic Caverns can be extra challenging, so I'm here to help you out with some strategies. If you don't already have it, you can find the game at the link below. So you're looking at a puzzle that looks a lot like this. It has 3 rows and 3 columns, and the numbers in each row and column multiply to produce the numbers on the ends. Let's label each of the numbers in spaces so it's easier to see what we're talking about. We're going to need to fill the numbers at the top of the puzzle, 3, 4, 5, 6, 7, 10, 11, 12, and 14, into the blank spaces A through I. To solve the puzzle, enter the cavern and help Umi out. Hey Umi, how's it going? Awesome. So how should we tackle this? Your first strategy might be to guess and check, multiplying the numbers at the top together until we find which ones make 462 or 385. This method might help you hone your multiplication skills, but in this case, it's not the most efficient way to tackle the puzzle. A robot could do those calculations for us, and we are not robots, we're mathematicians. So what should we do instead? Well, we can tackle this using 2 strategies. The first is divisibility rules. I'm not saying divisibility rules, I mean it does, but I'm talking about rules that we can use to determine whether one number is divisible by another. For example, you probably already know the divisibility rule for 2. A number is divisible by 2 if it's even. For instance, if we ask, is 360 divisible by 2? We can just ask, is 360 even? Since it is even, we know it is. You might not have heard of the divisibility rule for 3. If we ask, is 360 divisible by 3? We only have to find if its digits sum to a multiple of 3. That is, we have to add up 3 plus 6 plus 0. And since 3 plus 6 plus 0 is equal to 9, which is of course a multiple of 3, we know 360 itself is divisible by 3. The divisibility rule for 4 is another one you might not have heard of. To find if a number is divisible by 4, we only have to find if its final 2 digits are divisible by 4. So in the case of 360, 60 is divisible by 4 because 15 times 4 is equal to 60. So we know 360 must also be divisible by 4. The divisibility rule for 5 you might also have heard of. If a number is divisible by 5, it ends in a 0 or a 5. Since 360 ends in a 0, we know it's divisible by 5. The divisibility rule for 6 actually combines 2 divisibility rules we've already seen. It asks, is a number divisible by both 2 and 3? That is a number even, and do its digits add to a multiple of 3? Since we know that 360 is even, and 3 plus 6 plus 0 adds to 9, which is a multiple of 3, we know that 360 is divisible by both 2 and 3, and therefore divisible by 6. The divisibility rule for 9 is another fun one. It says, if the digits of a number add to a multiple of 9, it's divisible by 9. Since 3 plus 6 plus 0 is equal to 9, which is of course equal to 9 times 1, so it's a multiple of 9, we know 360 is divisible by 9. Finally, the divisibility rule for 10 is one you've almost certainly heard. A number is divisible by 10 if it ends in a 0. Since 360 ends in a 0, we know it has to be divisible by 10. Here's a handy chart that summarizes all of the divisibility rules that we've just talked about. Feel free to pause the video here to write down any divisibility rules that might be useful to you. So mathematicians actually have divisibility rules for every whole number. One tool to help us discover more divisibility rules is called prime factorization. When we use prime factorization, we find the recipe for a number with all of its essential ingredients. Think of breaking down a tower of Legos. When you've pulled all the bricks apart, you're left with a set of bricks that you can't cut up or pull apart any further, just like prime numbers. Just like Legos, you can put the building blocks that you get from prime factorization back together in a few different ways. But you'll always get the same number if you multiply all the prime factors together, just like you'll always have the same pile of Lego bricks, no matter what shape you make them take. For instance, take the number 24. We can use a factor tree to break it down. We know that because 2 plus 4 is equal to 6 and 6 is divisible by 3, we can factor out 3 as an ingredient. 3 is prime, we can't break it down any further, so we'll circle it to tell ourselves that it's prime. Now you have to multiply 3 times 8 to create 24, if we remember our multiplication facts. So we'll put 8 over on this other branch of the tree. 8, of course, is not prime. It can be broken down further into 4 times 2. So let's factor out 2, leaving us with 4, which breaks down even further into 2 times 2. All of those 2's, of course, are prime. Now we have all of the basic ingredients of 24, 1 3 and 3 2's. These 3 2's and 1 3 are the building blocks of the number 24, and in different combinations can show us all of the different ways to make 24, 12 times 2, 4 times 6, and so on. What about a big number, like the kind in Cryptic Caverns? Let's try one of the numbers from the puzzle, like 462. If we add up the digits, we get 12, so we know right off the bat that the number is divisible by 3. If we divide it by 3, we get, let me just do that in my head, 154. Using the divisibility rule for 2, which tells us that if a number is even, it's divisible by 2, we can divide out 2, leaving us with 77. Now, we don't have a divisibility rule that would apply to 77, but you're probably pretty up to speed on your multiplication facts, so you know that it's divisible by 11, which is prime. This means the other factor is 7, which is also prime, and we're done. So now we have this equation. These numbers are the only prime numbers that multiply to 462. Let's come back to the puzzle. What's our first step to solve it? Well, you'll probably notice that there are two numbers that end in 0, 200 in the K spot and 360 in the M spot. We know that the number 10 has to go somewhere in the puzzle in one of the answer slots, and that its divisibility rule is that a number divisible by 10 has to end in 0. Since there are no other numbers that end in 0, this means we can figure out exactly where 10 should go. Where do you think it should go? If you guessed D, you've got the hang of it. What about the divisibility rule for 5? It tells us that numbers which are divisible by 5 must end in a 0 or a 5. Are there any numbers here that do? 385 ends in 5, and no other number does. 200, though, does share an answer spot F with 385, and it ends in 0. Since this is the only spot at the intersection of two numbers which are divisible by 5, we know that 5 has to go here at F. We only have one spot left in the row for 200. What should go in it? Let's do the prime factorization of 200 real quick. We already know that it's divisible by 5, since we just filled in that factor. So let's factor that out. 5 is prime, so we can't break it down any further. That leaves us with 40. Since 40 ends in a 0, we can divide it by 10. Let's factor that out. 10 isn't prime, and we can break it down further into 2 and 5, which are both prime. What was left when we divided 40 by 10? It was 4, which we can break down into 2 and 2, both prime. If we come back to the puzzle, we can see that we've used 1, 5 already in the F spot, and 1, 5 and 1, 2 multiplied together to make 10 in our D spot. This means that we have 2 2s left, giving us 4 in the E spot. So now let's fill 4 into the E spot to finish the row. Nice job. So now we've figured out where 4, 5, and 10 go. Where do we go next? How about we look at one of our columns, maybe 385. If we do the prime factorization of 385 real quick, we know it's divisible by 5 because it ends in 5, so let's factor that out. 385 divided by 5, I just so happen to know off the top of my head, is 77. We already know that 77 is divisible by 11 and 7, which are both prime, and we're done. Coming back to the puzzle, we can see that we have two spots left in the column for 385, C and I. We've used the 5 in 385, so we know that there are only two prime factors left for us to use, 7 and 11. Therefore, we know that each of those prime factors has to take one of those spots. One has to go in spot C, and one has to go in spot I. Well, which goes where? We know from doing the prime factorization of 462 that 7 and 11 both go into 462, so either could go in spot I. Let's try C. Does 11 go into 504? Let's do the prime factorization of 504. Since 5 plus 0 plus 4 is 9, which is divisible by 9, we know that 504 itself is divisible by 9. 9 isn't prime, but it is divisible by 3, and what's left is 3. If we divide 504 by 9, we get 56. From our multiplication knowledge, we know that 56 is equal to 7 times 8. So we can divide out 7, which is prime. 8 breaks down into 2 times 4, which is 2 times 2. So we can see that 11 definitely doesn't go into 504. Since 11 doesn't go into 504, we know it can't go in spot C. This means we should put it in spot I, and the final factor of 385, 7, has to go in spot C. Now that we have the prime factorization of 504, we can look at what other factors we could use from it. We've used 7, so let's cross that out. We have 2 3s and 3 2s. So we could use the 3, the 6, or the 12 here, since you can get any of those numbers by multiplying 2s and 3s together. Let's think about the 3 for a minute. If we use 3 in either spot A or B, the other spot would have to incorporate all of the remaining factors, 3 times 2 times 2 times 2, which is 24. We don't have a 24 in the answer numbers, so this means we can't use 3 in either A or B because we can't use 24 in the other one. So we'll have to use 6 and 12. If we were to put 6 in spot A, you can see that we have spot D with 10 underneath it. So 6 times 10 is equal to 60. That means spot G would have to be equal to 360 divided by 60, which is 6. We can only use each of the answer numbers once, so we can't use 6 again. So A can't be 6 either. This means A has to be 12. It's the only number left that fits. Since 3 can't go in either A or B, B must be 6. Now we've used all of the prime factors of 504 to fill out that row. And we can solve the rest of the puzzle now too. 12 times 10 is 120, and it's easy to tell that 120 times 3 is 360. So we can put the 3 in G. This just leaves 14, which must go in H. If we remember our prime factorization for 462, this actually makes a lot of sense. 462 was divisible by both 7 and 2, so of course it should be divisible by 14 too. This suggests that a good divisibility rule for 14 might be that the number is divisible by both 2 and 7. And we're done. Nice job. Good luck as you get further into the cavern. You've got this.